All right, this lecture is on the conservation of energy. It says energy conservation is the foundation of energy independence. One thing that's wrong with that quote is energy is always conserved. It's not conserving energy, it's keeping it in a usable form more than anything. So the goals are that students can calculate energy using the law of conservation of energy, and they should understand the ramifications of the law of conservation of energy. So we've talked about mechanical energy for a system, and what that is the measure of the total energy in a system. So how much kinetic work, elastic potential, gravitational potential, how much total energy is there in a system. Okay, this example says, where does the coaster have the greatest mechanical energy? And you should realize that because of things that we learned at the beginning of this lecture and have been an ongoing theme throughout, it turns out there is no greatest mechanical energy. Because of the law of conservation of energy, we can say that the mechanical energy here is equal to the mechanical energy here. Now that can be somewhat counterintuitive to people because they say, well, I'm moving faster at the bottom, so I'm going to have more kinetic energy. And that is true, but you're going to have less potential energy. So because of the law of conservation of energy, there is no greatest mechanical energy because all points along the track are equal. So you should know that conservation of energy is never created or destroyed. It's only converted from one form to another. You can take kinetic and convert it to potential, and potential to work, and work to electrical. But that's expressed as E1 equals E2. So the energy you have in one situation has to equal the energy you have in a second situation. So earlier this year, we said that mass didn't have anything to do with the final velocity of an object. We did our kinematics motion equations. Mass was nowhere there, and that's somewhat counterintuitive. So we wanted to look at it using the law of conservation of energy and show why that's the case. So if you have an object that's above the surface of the Earth, it has potential energy due to gravity. Okay? When the object is about to strike the surface of the Earth, it has no potential energy due to gravity. Okay, the potential energy due to gravity is gone. When you originally hold the rock above the surface of the Earth, the object doesn't have any kinetic energy because it has a velocity of 0. But it does have kinetic energy at the bottom. So what we can say is the potential energy that I have at the top is equal to the kinetic energy that I have at the bottom. Now what does this have to do with final velocity? Remember, kinetic energy is the equation is the energy that has to do with velocity. So what we can do is we can say, okay, well, mass, gravity, height equals 1/2 mass velocity squared. And what you'll notice when you write that out is you'll say, oh, look, there's mass on both sides. Well, if you have a variable on two sides of an equation, it cancels out. And what you end up with is gravity times height equals 1/2 velocity squared. Or you can even kind of simplify this a little bit. You can say, well, you can't really simplify it. Okay, this question says, if an object with a mass of 5 kilograms is dropped from the height of 14 meters, determine its velocity as it strikes the ground. So we're looking for the final velocity is basically what we're looking for. We have a rock that's being dropped 14 meters above the surface of the Earth. If you were to look at the previous example, you'd realize that mass actually, although it's given as 5 kilograms, is actually irrelevant to this particular question. Instead, we can use the conservation of energy. Energy 1 equals energy 2, and the fact that before a rock is dropped, it has potential energy due to gravity, and at the bottom it has kinetic energy. Or we can say that PEG is equal to KE. When you do that, you can expand it even further, and you can say, okay, well, mass, gravity, height equals 1/2 mass velocity squared. Since you have mass in both terms, you can cancel it out. And what you're left with is GH equals 1/2 V squared. Well, you are given the height. The height that gave us was 14. You are given gravity, because we're going to assume that it's on Earth, and those are the only two factors that you need in order to solve for the velocity. So we can plug in, we can say 9.8, 14, 1/2 v squared. Multiply both sides by 2. When you do that, you're going to get 2 times 9.8 times 14. That's 274.4. But remember, what that represents v squared. So we have to take the square root of both sides, and what we get is 274.4, take the square root, we get 16.6. Now remember, when you take the square root of something, you're actually taking the plus or the minus. So this could be plus or minus 16 meters per second. Now, since we know that the object is going to be falling, we know that the correct answer is more than likely negative 16.6 meters per second, depending on how you've defined up and down. All right, this same example says a 5 kilogram ball is thrown vertically upward with a velocity of 20 meters per second. What is the maximum height achieved using the law of conservation of energy? Now, you could use the kinematics motion equations that we've talked about earlier, but it says specifically use the law of conservation of energy. So E1 equals E2. Now, whenever you're throwing something, you're imparting a kinetic energy to it. So to begin with, I have kinetic energy as the ball makes its way upward. When it reaches its highest point, the ball stops moving. So there is no kinetic energy in the second situation. Instead, what it has the potential to fall. So potential energy due to gravity. You notice this is the exact same thing that we did before with the rock falling and seeing how fast it hits the ground. Now we're saying, hey, we're going to throw it. We've got velocity. How high is it going to go? So we are trying to solve for h. Now, just like we had before, we have kinetic energy, which is 1/2 mv squared. We have potential energy due to gravity, which is mgh. Mass cancels out of both of those terms. So we have 1/2 velocity squared equals gravity times height. So let's look at our given information. We were given a 5 kilogram ball. Okay, that 5 kilogram ball has no relevance in this problem. G is 9.8. We are trying to solve for the height, and we were given a velocity to begin with of 20 meters per second. So we say 1/2 of 20 squared equals 9.8 h. Divide both sides by 9.8. So we say 0.5 times 20 squared divided by 9.8, and it gives us 20.4 meters is the height that the rock will go. Alright, this question says a 10 kilogram rock is dropped from a height of 10 meters onto a spring below. It says if the spring is known to have a spring constant of 100 newtons per meter, how far will the spring compress? So, there is an easier way to do this and a more difficult way to do this, and we are in this class more focused on the easier way to do it, but I will show you just a little bit of the more difficult way to do this just so that you have an idea of a more realistic solution. So we're going to start off with, we are trying to solve for how far the spring is compressed, which is our x value. We know that we can use conservation of energy. Since I know I have a spring and being dropped involved, I know I'm going to have potential energy due to gravity, and I'm going to have potential energy due to some sort of elastic situation. So here's basically what we have. You have a rock that's being dropped onto a spring, and you want to know how far that spring is actually compressed. Okay, the easy thing that we're going to do is we're going to say that when the rock drops to this point, all of its energy is converted into compressing the spring. So in other words, I'm going to say simply mgh is equal to 1/2 kx squared. Okay, and that's true for both situations, but I'm going to define this height right here as h, and then this right here is x. And it's actually a little bit more complicated than that, but let's go ahead and solve this, and then we'll talk through some complications. So you are given a mass of 10 kilograms. If you notice in this particular example, we can't simply cancel out the mass because it's not on both sides. We have that it's dropped from a height of 10 meters. We also have that the spring constant is known to have a value of 100 newtons per meter. So really, that's all I need to know, because I know gravity is 9.8, and I can say 10 times 9.8 times 10 equals 1/2 100 x squared. And when you do that, you can go ahead and start to simplify. We have 980, which is 10 times 9.8 times 10, equals 50 x squared. 1/2 times 100. Divide both sides by 50, and you get 19.6 equals x squared. You can then take the square root of both sides, and you can say this is 4.43. Now, for the more difficult solution to this particular question, we're just going to talk through it real quick, and I can show you real quickly how you can solve it, is this. Really, the rock doesn't fall just this h. It actually falls h plus x, because the rock will continue to fall. Even when it touches the spring, it will keep going down until it's compressed a certain, till the limit of the spring. So really, this should actually be mg, and then I'm going to go ahead and plug in what h is, 10 plus the displacement of the spring. Now, the reason why we didn't solve this way is you can see that when you plug in your numbers, go ahead and plug the numbers in, it creates a problem. And that problem is you have x on this side and you have x squared over here, and then you're going to have some other number right here. What this sets up is it would set up a quadratic equation that you would have to solve. Now, it's not terribly more difficult than things we've already done, but it is a little bit further than we want to go in this class. Just be aware that this is a more accurate solution when you account for this than what we did in the previous solution. Okay, this question says a spring of 1,000 newtons per meter is compressed 28 centimeters. How fast will a 50-gram marble move if fired from the spring? So basically, we have like the CPO marble launcher, where you have the marble on a spring, and it's compressed a total of 28 centimeters from its original length. So now we say, I want to know how fast, velocity is a measure of how fast that this marble or this ball will be moving. So I know that I've got two different types of energies. Because I'm talking about a spring, I know that I'm going to have potential energy elastic involved. And also, because I know that I'm trying to figure out how fast something's moving, I know that I'm going to have kinetic energy involved. So with those two things kind of defined for me, I can say, well, now what information am I given? You're given a spring constant value of 1,000 newtons per meter. You're given a compression of 0.28 meters. You should recognize that that was in centimeters. You're also given that the mass of the marble is 50 grams. Now, it's been a while since you've really had mass given to you in grams, but you know you're supposed to convert that to kilograms. Mass is the only thing where the base unit is a kilogram instead of just a standard gram or something, meter or something along those lines. So this should be 0.05 kilograms. We had to move the decimal over 3 places. So now that we have our given information, we can now say, all right, now we can plug it in here. So potential energy elastic is 1/2 k x squared. Kinetic energy is 1/2 mass velocity squared. Now, I can't cancel out mass, which is what I'm used to doing, but if you look, I can cancel out the 1/2 terms. Because I have it on both sides, the 1/2 goes away. Doesn't really do a whole lot to simplify the calculation, but it'll work for now. So now we have 1,000, and then we have 0.28 squared on the left, and on the right we have 0.05, and then we have v squared. You do have to be careful about this. For some reason, when I have x squared and v squared, a lot of people think you can cancel out the squared term. You can't do that. Okay, mathematically that doesn't make any sense. Now, if they were the same, if this was x squared and that was x squared, it would work. But since these are two different variables, you can't take the square away. So now we divide both sides by 0.05. And when we do that, we get 1,000 times 0.28 squared divided by 0.05. And we get 1568 equals v squared. We take the square root of both sides, and we get 39.6 meters per second is my velocity. So if you were to compress a marble on a spring, it would come out pretty fast, in excess of 100 miles per hour at 40 meters per second. This one says a pendulum with length 2 meters is pulled such that the angle between the starting point and the equilibrium position is 20 degrees. It says the pendulum bob has a mass of 2 kilograms. What is the velocity as it crosses the equilibrium position? So it doesn't look like you're given a whole lot of information there, but you are given more than you realize. This is going to be a particularly math-intensive question. You've got to remember all the math that we've used so far, as well as the conservation of energy. So we are basically looking for the velocity, and we're looking for the velocity of the object in the downward position. Now, I know that I raise the pendulum bob such that this angle right here is 20 degrees. So I'm going to go ahead and just pull this out real quick, and I'm going to say, okay, that means I have a 20 degree angle, and I also have this right here is the length of the string. If you look, the string on the pendulum bob isn't going to change its length as it's moved up. So this right here is 2 meters. So I have the hypotenuse of a triangle, and I have the angle of a triangle, and that allows me to calculate the sides of a triangle. This side of the triangle has no real relevance, but this side definitely does. So I want to go ahead and calculate this side right here. Most people think, okay, well, it's going to be sine because I'm trying to solve for the y component. Well, that's usually when you have this angle right here. So you have a couple of choices. What I like to do is I like to say, okay, if this is 20 degrees, this is 90 degrees, that means this has to be 70 degrees. And what I can do then is I can say, okay, sine of 70 times 2 would give me this side right here. So let's go ahead and do that real quick in our solution. We say 2 times the sine of 70. And you can see how I got 70 is just 20 and 70 have to add up to 90 because you have a 90 degree angle here. So if I have that, 2 times the sine of 70, and that gives me 1.88. So this side of the triangle is 1.88. And you say, okay, well, what does that have to do with anything? If you look back to our original drawing, this is the triangle that we're talking about. We saw this as 1.88. But the height, the difference in the height between these two objects is this distance right here. Remember, if the entire string length is 2, and then this one has a vertical position of 1.88, you can now solve and you can say, okay, well that means that the height, the discrepancy between these two things right here, would be equal to 2, which is the whole length of the string, minus this 1.88, which would give us a value of 0.12 meters. Okay, that's the tough part of this. Once you have that, the rest of the question is very, very easy. Conservation of energy, E1 equals E2. Talking specifically about potential energy, because gravity pulls it down. And then you also have 1/2 mass velocity squared, which is the kinetic energy. So we can say mass cancels out. We have gravity, which is 9.8, times the height, which was the tough part, finding 0.12. And then on the other side, we have equals 1/2 what I'm trying to find squared. So what we do is we multiply both sides by 2, and when we do that, we get 2 times 9.8 times 0.12, and that gives us a value of 2.352. Remember that equals v squared, so we have to take the square root of both sides, and when we do that, we get 1.53 meters per second. Okay, this is the last question for this lecture, and it is a doozy. It's very, very difficult to do. It says, a roller coaster begins at a highest hill 100 meters above the surface. And then it says, what is the centripetal acceleration felt by a rider at point A? So you have the roller coaster goes down, it goes through a loop, and you want to know what the centripetal acceleration is right there. And you may be asking yourself, well, centripetal acceleration, that's something we talked about before. It doesn't really have anything to do with energy. And that's true to some extent. We are trying to solve for centripetal acceleration. Remember, or if you don't remember, look at the formula chart. The formula that we have for centripetal acceleration is equal to the velocity squared divided by the radius. Now, if you look at the drawing, you actually have the radius, and that's very, very good. We say that the radius of this particular loop was 20 meters. Unfortunately, that is the only piece of information that I was given. Okay? So somehow I've got to derive what this velocity term is. And if you think about it, you should be able to realize that what I'm basically doing is I'm converting potential energy to kinetic energy. Now, what is different about this is that I'm not going from the surface or from the high point to the surface point. Instead, I'm going from the high point to some middle point right here. In fact, that middle point I know would be the whole diameter of the loop. If the radius is 20, I know that that height is 40. So now what I'm going to do is I'm going to apply the law of conservation of energy. I'm going to say E1 equals E2. But instead of just saying potential energy equals kinetic energy, can't do that because there's also a potential energy term here. Okay, I'm going to call this PEG, but then I'm just going to put a little 2 above it. And the reason why I'm putting the 2 there is that's the potential energy at the second point. Okay, you can distinguish it by putting, some people like to put a prime there, or put an F here, or a 2. However, you can keep these two potential energies different. Okay, this one is involved for this height, this one is involved for this height. So now we say mass, gravity, I'm going to go ahead and put H1 just to let me know that's the first height. Then I'm going to say equals 1/2 mass velocity squared plus mg H2. Lets me know that I'm talking about the second height. If you look, mass is in every one of those terms. So even though you are not given the mass of the roller coaster, it's irrelevant. It's in all the terms, it cancels out. You know gravity. Gravity is 9.8. The height of the first one was given to you of 100 meters. On the other side, 1/2 velocity squared. That's what I want to know to be able to calculate centripetal acceleration. Plus 9.8, and then H2 is 40 meters. So now we can say 9.8 times 100 and 9.8 times 40. So this term right here is 980, and this term right here is 392. I'm going to take this and I'm going to move it to the other side. So I get 980 minus 392 equals 1/2 v squared. Or 980 minus 392. Now what I'm going to do is I'm going to multiply both sides by 2. And I get 1176 equals v squared. Now I could go from here and I could go ahead and solve for the velocity if I wanted to. But really there's no point because in the formula I have centripetal acceleration is equal to velocity squared, which is what I've got right here. So now what I want to do is I want to go ahead and say, okay, well, centripetal acceleration is equal to 1176, which is the velocity squared, divided by the radius, which was 20. So when you do that, you get a centripetal acceleration of 58.8 meters per second squared. Now just to kind of put that in perspective, that would mean if you were at that point, you would feel something about 6 times stronger than gravity. So you would feel 6 times heavier in your seat if this situation were right. Now, that might actually cause some people to pass out. This is a very difficult question. It involves stuff that we learned a while ago with circles, conservation of energy when you don't cancel out one of them, you have two energies in one situation equaling another one. This is a tough problem, but you should be able to understand the principles that are involved in this. So now you should be able to calculate, you should be comfortable calculating energy for using different types of energy and the law of conservation of energy. The key thing is to look for what types of energy are involved or what information is given to you. For example, if the object is moving, there's got to be kinetic. If there's some sort of spring involved or stretch, you know it's got to be elastic. You have to look for keywords to be able to identify what types of energy you are supposed to be using. You should also understand that energy is always conserved. The key thing is just to keep it in usable forms.